Hello, this is Satbir. The topic of our discussion in this video tutorial is bounded sequence. What is a bounded sequence? A sequence xn is said to be or is a bounded sequence if and only if, so this is a symbol of if and only if, we can find, or in other words, there exists a real number m which is strictly positive, so that the absolute value of each term of the sequence is less than or is equal to that real number m. And this is true for all values of m belongs to the set of natural number. So this is the definition of a bounded sequence. Let me first give you the recall of a very important property of the absolute value function. So the absolute value of a real number x, if it is a less than or is equal to another real number a, this implies that the real number x is between the value of the real number of minus a and a. So this is an important property which we will use this in this course a lot. Now, if I use this property on this definition, so this definition basically turn into that the absolute value of xn is less than or is equal to m, it will become the each term of the sequence, they are between the real number minus m and m, and this is a true for all n belongs to the set of natural number. Now, using this statement, I will draw the picture of this definition so we can basically see more intuitively what does mean by a bounded sequence. So picture. So in the picture, I'm going to plot the term of the sequence on the y-axis, and here is the domain of the sequence, which is n, and here I will plot the term of the sequence. So a sequence is said to be bounded if you can find the two real number, capital M, and the negative of that. Basically, it's one real number, just the positive M and then the negative M. And the each term of the sequence, they are bound by these two real number. So each term of the sequence, it just stay, it cannot go above or it cannot go below these two real number, which is m and minus m. So this is the intuitively meaning of a sequence is bounded if each term of the sequence they are bound by a number, the negative of m and the positive of m. Now let me give you a few example of bounded sequence and also the sequence which are not bounded. So our first example is xn. Let's suppose xn sequence is 1 over n. As you can see that if I plot the term of the sequence, it will be first term will be 1, then 1 half, then 1 half, and it will keep going closer and closer to 0. So as I can see, I can find the two number, which is a 1 here and also the negative 1. And all the term of the sequence is lies between these two limits. Therefore, this sequence xn, it is a bounded, and that number m is in fact is 1, and this is bound by the number 1. One more example. This time I'm going to take my sequence xn minus 1 to the power n. If I draw the picture of the term of the sequence, as you can see that if I plug 1, I will get negative 1, and then positive 1, then negative 1, positive 1. So the term of the sequences, they are oscillating between 1 and negative 1. So I can say that all the term of the sequence, they are in these limit, or in other words, the absolute value of this sequence, each term of the sequence is less than 1. So this is a bounded sequence. An example of an unbounded sequence, let's suppose xn n square. This is an unbounded sequence. As you can see that if you plot the term of this sequence, the very first term will be 1, then it will be a 4, and so on. So it will be keep going up and it will hit the infinity. There will be no real number which will contains all the term of this sequence. So there does not exist any real number m which will bound or all the term of the sequence. Therefore, this sequence is unbounded. So not bounded is called unbounded. So this sequence is unbounded sequence. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will prove a very important theorem. The statement of this theorem is every convergent sequence is bounded. I will use the direct method to prove this theorem. So proof. The first I will write that what is given and what I want to show. And the direct proof, the meaning of the direct proof is I'm going to start from what is a given, and by writing some logical statement, I want to reach what I want to show. So let's first write down what is a given. So given is a convergent sequence. Let's suppose xn is a sequence which is a convergent. If it is a convergence, it must be converging to some real number L. So this is a given. And we want to show that this sequence is bounded, or in other words, mathematically, we want to find m, which is strictly positive, so that the each term, the absolute value of the each term of the sequence is less than or equal to that m, and that is true for all natural number. So this is a given, and this is what we want to show. Now I will write the series of logical statement starting from the given, and my goal is to reach what I want to show. So let's start. Their first statement is xn converges to L. And what does mean in mathematically? By definition, it is there exists for all epsilon positive, there exists a natural number n, which is belong to the set of natural numbers, so that the difference between the general term of the sequence and L is less than epsilon whenever n is bigger than or is equal to the capital N. This is the meaning. A sequence is converges to a limit L by definition. So this implies this statement. Since this statement is true for all epsilon, so it must also be true for one particular epsilon. So take epsilon, the value of the epsilon 1, and this will implies, I'm going to rewrite this statement again. There exists n belong to the set of natural numbers, so that this is symbol of so that x n minus L is less than 1, so that value of the epsilon when n is bigger than or is equal to n. Now I will use this important property of the absolute value function. So this implies minus 1 is less than x n minus L less than 1 when n is bigger than or equal to capital N. I will add L on both sides, so it will be L minus 1 less than is equal to xn less than is equal to L plus 1 when n is greater than or equal to this capital N. And what actually this means is the each term of the sequence are between L minus 1 and L plus 1 when n is bigger than or is equal to capital N. or in other words, the absolute value of this number, which is xn, it must be less than is equal to the maximum of these two numbers. If I take the maximum of L minus 1 and L plus 1, the absolute value of the each term of this sequence xn must be less than or is equal to the maximum of these two numbers. Or in other words, what this mean is, it means this sequence xn is bounded, but it is bounded for all value of little n, which is bigger than or is equal to n. So we prove half of the theorem that the sequence is bounded when n is bigger than or is equal to n. And now we need to show that the sequence is also bounded, that each term of the sequence is also bounded when n is between 1 to n minus 1. So therefore, I also need to show for n for 1 less than is equal to n less than is equal to n minus 1, each term of the sequence is also bounded. So for 1 less than is equal to n less than n minus 1, I'm going to consider this set, which is a x1, absolute value of x1, absolute value of x2. So they are n minus 1 first term of the sequence, and I construct a set out of these terms. And clearly this set is a finite set of real number. And it is intuitively clear that if a set is a finite subset of real number, it must have a maximum. So this implies this set has a maximum number, which will be also a real number. I'm going to call that maximum number, let's say k. The k is the maximum of that set. If k is the maximum, it means each term of this set, which is xn, less than or equal to that the maximum number k, when n lies between 1 to n minus 1. Actually, this proves that when the sequence, the term of the sequence which are from 1 to n minus 1, they are also bounded, and they are bound by this number k. Now what I will do, that I will combine this inequality and also this inequality, because the one inequality says where inequality is true when n is greater than or is equal to capital N, and this inequality is true when n is less than or equal to n minus 1. So I can combine both of them. So in order to combine, first I will choose. So I'm going to choose my m as the maximum of this number k, and L minus 1 and L plus 1. Then these two inequalities will hold for that m, because I choose the largest among all these three numbers. So therefore, this implies the absolute value xn will be less than or is equal to that number m, and this will be true for values of n which are bigger than n, and also the values of n which are strictly less than n. Or in other words, this is true for all n belongs to the set of natural number. And this is basically what we would like to show. As you can see, this is I wanted to show. So this complete the proof of this theorem. So that was a direct proof, which I start from what is a given, and I write some logical statement to reach to my goal, which I need to prove. Next, we will show that the converse of the previous theorem is not true. That is, not every bounded sequence is convergent. So we proved that in the previous theorem that every convergent sequence is bounded. But now we will prove the reverse direction of this statement is not true. That is, not every bounded sequence. If you have a bounded sequence, this sequence may or may not be convergent. In order to prove that a converse of any theorem is not true, all we have to do is we have to find an example which satisfies the statement of the converse. Or in other word, what we need to do is we need to find a sequence which is bounded but not convergent. So this is called a counting example. That means we need to find an example which contradicts the converse of the theorem. So let's find a sequence. We need to basically construct or find a sequence which is bounded. So as I show you in the previous example, the sequence is bounded. And we also know that the sequence is not convergent. I showed that in my previous video. So this sequence is bounded, but we also know that the xn is not a convergent sequence. So we have an accounting example which shows that the sequence is bounded, but it is not convergent. Here I have another quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.